Okay, thank you. So, hello everyone, my name is Julien Ferry. I'm a PhD student at the Laboratory for Analysis and Architecture of Systems, which is a laboratory part of the French National Center for Scientific Research in Toulouse, France. And I'm going to present my work on the use of integer linear programming methods to learn optimal fair rule lists. In the first part of my presentation, I will introduce the necessary background and notation. Then I will present our contribution, which in a nutshell consists in using integer linear programming methods to prune the search space of an interpretable fair learning algorithm. Then I will provide experimental results, and finally I will conclude. In this first section, I will first introduce the notation that will be used for this presentation. Then I will show how we can quantify unfairness in machine learning. I will introduce the type of interpretable models that we'll use today, that are rule list models, and I will present the algorithm we'll use to learn fair rule lists. We are interested in the binary classification problem, where we want to learn a mapping from a set of attributes to a space of labels, which is binary. So we are given a classifier, a dataset E, and our objective is to learn a classifier, a classification function, mapping the attribute space to the label space. We consider that the dataset is partitioned into a set of positively labeled examples and a set of negatively labeled examples, because we perform binary classification. And similarly, we consider that the dataset is partitioned into a protected group and an unprotected group. The intuition is that these different groups of a population differ only in the value of some sensitive attributes that can be gender, age, or race. And so we'll use these groups to quantify unfairness, as I will show later. Finally, we will use this notation to denote the number of true positive examples given the predictions of classifier C on dataset E for protected group H. And we will use a similar notation for the number of false negative examples, true negative examples, and false negative examples. There are several ways of quantifying unfairness in machine learning, and today we'll consider group fairness notions, also called statistical fairness notions. Their main idea is to ensure that some statistical measure, function of the confusion matrix of a classifier, differs by no more than a given threshold between different protected groups. Again, because the only difference between these subgroups of the population is the value of some sensitive attributes. There's no reason for a classifier to treat individuals from these different groups differently. And this is why we will try to match this statistical measure between the different groups. So depending on the particular statistical measures that we try to equalize across the different groups, we can define different metrics. So in this table, we summarize the metrics that are the most used in the literature. So we will use all these metrics in our experiments. But for this presentation, we can focus on the first one, which is called the equal opportunity metric. And as you can see, it tries to match the true positive rates between the different protected groups, so the protected group and the unprotected group. And formally, we want the difference between these two things to be no more than what we call an unfairness tolerance, epsilon. Regarding interpretability, in this talk, we will use rule list models. So rule list is a type of classifiers formed by an ordered list of if-then rules followed by a default decision. So here you have an example rule list. The set of ordered rules is called a prefix. And at the end of the prefix, you just have to add a default decision to get a rule list. So this is considered an interpretable model. And to classify an example given a rule list is rather straightforward. You have to apply the rules sequentially. Whenever the antecedent of a rule matches, you just have to return the associated consequence. And at the end of the prefix evaluation, if none of the rules matched, you return the default decision. Different methods have been proposed to learn rule list models, and among them, CORELS is a branch and bound algorithm, which learns optimal rule lists minimizing this objective function, which is simply the weighted sum of the classification error and the length of the rule list. So here, hyperparameter lambda is an hyperparameter controlling the trade-off between accuracy and sparsity. A couple years ago, we proposed FAIR CORELS as a bi-objective extension of CORELS. addressing this constraint optimization problem. So we want to learn rule lists minimizing the same objective function, but now they also have to respect some fairness constraints defined using one of the metrics that I introduced in table 1. Just like correls, fair correls represents the search space of rule lists using a prefix tree. So here you have an example prefix tree for a dataset with 4 attributes. It uses several bounds and different exploration strategies to explore this tree efficiently. So to understand the structure of this search space, here you have an example rule list, and it corresponds to this node of the tree because the first rule uses the attribute gender female, the second one is attribute age lesser or equal to 25. So if you add a decision to each of these rules, and then you add a default decision, then you get the corresponding rule list. So in this tree, each node corresponds to a prefix and the rule list if you add a default decision. And this tree encodes the set of all possible rule lists that can be built using these attributes. The problem with the fair correls algorithm is that it's mainly an incremental extension of correls where the search space is explored in this way. The only difference is that before updating the current best solution, we check whether it satisfies a fairness constraint. If it does not, we don't perform the operation. But because we are enforcing fairness constraints, we modify the set of acceptable solutions, and the search space, this prefix tree, is considerably harder to explore. And in these conditions, the original branch and bounds don't work very well. More generally, the problem of learning optimal interpretable models under constraints, such as fairness constraints, has been identified as one of the main technical challenges towards the development of interpretable machine learning. So the approach I'm going to propose can be seen as one particular technical solution to this more general technical challenge. Okay, so now I'm going to introduce the approach we propose to prune this prefix tree. I'll first give the intuition of our contribution, then I will present the integer linear programming model that will be used, and I will explain how we can integrate it within the exploration. So here you have an example prefix tree, an example prefix delta 1. So this is just another set of rules. You have an example rule list, which is called an extension of the prefix. So basically, it means that we took the prefix, we added some rules to form a longer prefix, a default decision, and we obtain a rule list. And you have an example data set. What we can see is that each example of the data set can be either determined by the prefix or not. For example E1 will be determined by the first rule of delta 1 because it has the attribute gender female. And so it will be predicted high. And because its true label is high, it's a true positive example. On the other side, we see that example E2 will not be determined by prefix delta 1. What is sure is that all examples determined by delta 1 will also be determined by any extension of delta 1, and they will have the same classification. So here we know that any extension of delta 1 will have at least one positive example, which is E1. And by symmetry, we know that it can have at most number of examples in the dataset, -1 false negative examples. And here is our idea. At each node of fair correls prefix tree, which corresponds, as we saw earlier, to a prefix, we check whether it is possible that an extension of this prefix simultaneously improves the objective function and meets the fairness requirement given the prefix predictions. If this is not possible, we can prune the entire subtree. Here is the integer linear programming model that we can use to do so. It takes as input the prefix predictions, and we only use 4 variables here. So we need 2 variables to model the confusion matrix of the classifier for the protected group and 2 others for the unprotected group. We see that the bounds of these variables, the domains of these variables are updated depending on the prefix predictions, as I mentioned earlier. And then, because we modeled the confusion matrix, we can just set the constraints that we want to meet on this confusion matrix. So this constraint is a constraint on the number of well-classified examples. So this is the number of well-classified examples. We can set U to a tight value, ensuring that we improve the objective function. L, and we can set U to a tight value which corresponds to the highest number of examples that can be well classified given the errors made by delta and the inconsistencies of the data set. And the second constraint is simply the fairness constraint. So this is exactly the constraint that was shown in table 1 at the beginning of my presentation. If we want to consider another metric, so here it's the equal opportunity metric constraint, but if we want to consider an additional fairness metric, we just have to plug in another constraint, and the model is the same. So if there is a solution to this integer linear programming model, it means that there exists a classification function consistent with prefix delta's predictions that simultaneously improves the objective function and satisfies the fairness constraint. But if there is no solution to this model, it means that there's no classification function, so no rule list in particular, that can improve the objective function and meet the fairness constraints at the same time while being consistent with prefix delta's prediction. So in this case, we can prune the entire subtree corresponding to this prefix.
If there is a solution, it says that there could exist,
yes,
right? But not
right.
that there does not.
No, we don't know if there exists a classification function, but we don't know if there exists a rule list corresponding to this classification function. But as the interesting case here is when there's no solution, because in this case, we can perform the pruning. So I just described the pruning variant where at each node of the prefix tree that I previously showed, we solve the integer linear programming model, and if there's no solution, we prune the entire subtree. We can imagine using the integer linear programming model to also guide the search of the tree. To do this, we add an objective function to the integer linear programming model. So this objective function is here. It's the number of well-classified examples. So now, if there's no solution to the ILP, again, we can prune the entire subtree. But now, if there's a solution, we get another information, which is how far we can improve the objective function while also meeting the fairness requirement. So we get a lower bound on the objective function, and we can use this lower bound to order the priority queue and guide the exploration towards the most promising regions of the search space. Okay, so now I'm going to provide some experimental results using our proposed approaches. We implemented the ILP models using the CPLEX solver. And in these experiments, we will compare 4 different approaches. So the first one is the original Ferry-Quarles algorithm using a breadth-first search. So this is the baseline method. We then compare 2 integrations of a pruning approach, an eager approach and a lazy approach, both using breadth-first search. So in a nutshell, the eager approach calls the solver to perform the pruning as soon as possible to limit the growth of the tree as much as possible, while the lazy approach does the contrary. It waits as much as possible to call the solver. Formally, the eager approach calls the solver before inserting a node into the priority queue, and the lazy approach does the contrary. It first inserts the node, and whenever the node is taken out of the priority queue, it performs the pruning. And the fourth approach corresponds to the guiding approach that I presented, where we perform an eager pruning, but we also guide the search depending on the ILP objective function. Okay, we compare these 4 approaches on 2 data sets that are widely used in the fairness community, that are Compass and German credit. We compare these 4 approaches on the 4 metrics of table 1. Here, I will only report results for the equal opportunity metric, but results for the other metrics gives the same trends. We set for each experiment a maximum memory use and a maximum CPU time, and we run each experiment 100 times using different random parameters, and we report average results. So in a nutshell, the Compass dataset, the task is to predict recidivism, and the sensitive attribute we consider here is related to race. And the German credit dataset, the task is to predict good or bad credit score, and the sensitive attribute we consider here is age, low or high, depending on the median. So here we can see the results for the Compass dataset and the German credit dataset. And what we see is the CPU time as a function of the percentage of instances solved to optimality. What we observe here is that the original Ferry algorithm, or baseline method in blue, never proves optimality for any instances here, and only proves optimality for a few instances here, and still requires a lot of time to do so. On the contrary, all our proposed approaches are able to reach and prove optimality for all instances in these experiments, and most of them here, and they are way faster than the original baseline algorithm. If we compare our proposed approaches one with the other, we see that overall the lazy approach is not interesting if our objective is to perform the entire search and reach and prove the optimality, which is what we expected. If we compare the eager and ILP guided approaches, we have an interesting result. So the red and the green curve correspond to these methods. The only difference results in the guiding because they perform exactly the same pruning. But the difference is that the red one tries to guide the search, guide the exploration. So we see that in this experiment, the guiding is really beneficial. It speeds up convergence a lot, which is not the case at all in this one. And for all experiments, we observed this. The guiding was either very highly beneficial or in some experiments, counter-beneficial. Here, I provide the experimental results on another dimension, which is convergence speed. So we see the CPU time as a function of the normalized objective function quality. And what we observe is that in the earlier stages of exploration, the fastest method is the original Ferry algorithm in blue. This is because our different methods have to perform calls to a solver, which at the beginning of the exploration takes time. However, we observe that given sufficient time, and because the scale is logarithmic, this time is in practice some seconds, the performed pruning becomes beneficial, like the calls to solver payoff, and all our methods are able to reach better objective function values. If we compare our proposed approaches one with the other, we observe that the lazy approach has a high interest at the beginning of the exploration. It offers a good trade-off between aggressive pruning performed by the eager approach and no pruning at all, as seen with the baseline approach. Again, with the guiding method, we observe that it's highly counter-beneficial in these experiments and highly beneficial here because it speeds up convergence a lot, as we can observe here. Okay, so to conclude, we proposed a method based on integer linear programming models to prune the search space of Ferry. Our approach leverages jointly accuracy and fairness. It leads to significant improvements on all evaluated criteria. So we can reach better objective function values. We can certify the optimality of the produced solutions, and we can do all this using less time and less memory. I didn't provide results for memory, but they are in the paper. One big advantage of our approach is that due to its declarative nature, it can easily be extended to more general setups. We can also easily plug in additional constraints. Future works include considering other machine learning algorithms or other types of models, but also pursuing the efforts we attempted with the ILP guided approach, because we observed that in some situations, the guiding we perform can be highly beneficial. So the source code of the improved version of the Ferry algorithm is available online. You can also install it easily using PyP. I want to mention that in the paper, we also propose an additional data structure that intuitively cuts the prefix tree symmetries while still guaranteeing optimality. And we observe that this new data structure is very complementary with this approach. And so while using both the proposed pruning and this new data structure, we can solve in bigger instances to optimality, like data sets with tens of thousands of examples. Okay, thank you for your attention.
Questions? You want first?
Did you try a LP relaxation rather than a MILP at every stage?
I didn't. I could have done that. So instead of using this model, we solve its linear relaxation. So the idea is that at each node, the pruning will be faster, but it will be weaker, right? We didn't try this. In practice, this can be solved in some milliseconds with a well-optimized code. We could have, but we didn't.
Yeah, I suspect it'll be almost the same. Maybe it doesn't make much difference because the MILP will find out it gets the LP solution will be your integer anyway. But it seems to me with these big numbers that there's no reason to use MILP.
Well, at least the performance results seem that the MILP approach is slower in the beginning at least, so it could still benefit from the LP. Actually, looking at that, if you go to your results, like with the runtimes, yeah, here, so you can see that in the beginning, your ILP approach is really not benefiting much, it's actually not finding good solutions for quite a while. And I think it's because your prefixes are essentially too short, so they're not giving any information to the ILP. So you might get much better results by just like delaying when you turn on the ILP pruning, and it will look way better. So this way it will have a much better anytime performance to your approach.
Yeah.
Consider doing this? Or?
We imagine doing this, like, because the thing is, as you mentioned, the deeper we are in the tree, the stronger is the pruning, because the domains of the variables are more constrained. But the thing is also, the higher the pruning occurs, the more nodes we prune. So I performed some experiments while we decided to start the pruning only after some levels of exploration. The results were not better, so I finally didn't use them. But yeah, definitely deciding when to begin pruning will be an interesting thing, to not slow the exploration as we can see at the beginning. But again, because the scale is logarithmic, in practice, the stage where the original approach yields better objective function values is quite short. It's really the only beginning of the exploration.
And then in terms of the breadth first search, I mean, this seems like a very vanilla approach. So have you explored any kind of heuristics or branching heuristics? Yeah.
So we tried a BFS. We also tried the kind of default policy of the Correl's algorithm, which is guiding by the objective function. We tried a bunch of methods, and we only report results for the BFS here because these were the best ones. But for all methods, the results show the same result. Like, yeah, while performing a best first search, our pruning methods were also better to prove optimality. Yeah, the ordering of the methods were always the same, but for each method, the results using BFS were always the best. And the reason for this is when we try to guide exploration using the original best first search policies, we guide exploration towards the wrong directions. So finally, doing a breadth first search, like trying to explore everywhere without knowing where to explore in particular, seems to be the best policy in this case.
Well, that seems to be like a low-hanging fruit for somebody. Possibly no heuristic whatsoever for this. There has to be some heuristic.
This is what we attempted to do with the ILP guided approach. But we can do heuristics for accuracy. We can do heuristics for fairness. We can try to combine them somehow, but it's considering them together not easy. And this is what we tried to do with this approach. And as we saw, it sometimes works, sometimes not. Another reason for these results might be that when we perform the ILP guiding approach, we have to solve an optimization problem rather than only a feasibility problem. So each call to the solver here with a red curve is also takes more time and is also more challenging.
So most likely the best node selection heuristic might not be the ILP.
Yeah.
It could be something.
Or it brings you back to the LP.
Exactly.
Yeah.
Yeah, so
Yes.
maybe related to that. So there are some methods doing just pure integer programming, like column generation, for these kinds of things. Have you compared all that? Do you have a sense of whether this problem-specific formulation is better, like the Correl's kind of approach versus integer programming?
So there are some integer programming approaches to learn rule lists, but usually they're not as scalable as Correl's. Like even without considering the fairness constraints, they can only be used on datasets with a few hundred examples. Correl's is way more scalable than them due to the way it presents the prefix. And yeah, I didn't detail the Correl's algorithm, but it uses a bunch of data structures, optimized pruning strategies. While we first performed fair Correl's, we proposed fair Correl's, we had to disable part of these data structures to maintain the guarantee of optimality. And what we did with the data structures that I mentioned quickly in the conclusion was modifying the original data structures to perform a weaker pruning on the symmetries, but being able to still guarantee optimality of the produced models.
All right, I think we will wrap up the session here. Thank you very much.